And we were doing some programming examples of Turing machines. Now, when you do the full program, which means you're really starting with a problem statement and then you think of a high-level idea, just as you would if you were doing a program in a modern computer language like Fortran or something that you all use, right? Fortran 4. Oh no, now we're on to Algol or PL1. Anyway, those are the languages I used when I was your age. You know, so you get the general idea first, and then you try to translate it into the programming language, and then that gets translated into assembly language, and that gets translated into machine language, and so on. But we have to do all of those stages when we're thinking about designing a Turing machine for a particular problem, and it ultimately gets very tedious. So just as in programming or in thinking about programs and algorithms, you want to develop an ability to think at a higher level of description, knowing that you could take that level of algorithmic description and turn it into an actual full-fledged Turing machine. The last time we did that sort of all the way down, we didn't write the transition rules. We wrote a diagram that showed what those transition rules were, and that was for the problem of determining whether a number was a power of 2. Okay, so today we're going to start by looking at another problem, and we're not going to even go down to that full level of writing out the diagram, and certainly not the transition rules. But we'll just describe it at a higher level, and hopefully everybody can see at this point you through your intuition you developed as a programmer, and now your intuition from your limited exposure to Turing machines and your exposure to finite state machines, you can see how you would go all the way down to the transition rules if you had to. Okay, so it's not something you could do I would expect you to do on an exam. It just takes too much time. But you could do that as a homework exercise. It's tedious, but it's useful to go through a few of those tedious kinds of things just so you really fully develop your intuition. Okay, so the language, I think I wrote this up last time just as we were ending. You're going to take in strings that consist of some number of A's, we represent by I, some number of B's, which we represent by J, and some number of C's that we represent by K. And what we want is the property that I times J equals K. And we'll assume that all of these are greater than or equal to 1. Okay? So that's the language C that we're interested in. So, for example, if we have A, B, 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 and if this string is in the language, what should C be? What should the rest of the string be? 6 C's. Yeah, 6 C's. 1, 2, 3, 4, 5, 6. So that's a string that is in the language B. If we had A, B, C, C, that's a string that's not in the language because 1 times 1 is not equal to 2. Okay? So, all right, so we want a Turing machine which will take in strings that look like some number of A's, some number of B's, some number of C's on their input tape. So the Turing machine is going to be like this. The input tape is over here. Some number of A's, some number of B's, some number of C's, and it's going to accept if it's in this language C, and otherwise we want it to reject. Okay. So what's the first thing that this Turing machine probably should do? What's a good idea for this Turing machine to do? Actually, I kind of tricked you because I said we're going to take in input that looks like some number of A's, some number of B's, and some number of C's. Well, that's the right case. That's a necessary condition for that string to be in the language C. Okay, but there might be input which is not even in that form. So first thing that the Turing machine probably should do, because it's a simple thing and it's necessary that the string be in that form is just scan across and make sure that what's looking at is some number of A's, some number of B's, and some number of C's. Okay? Well, that's something you can do even with a DFA, right? I mean, you have some state, and you're looking at some number of A's, okay? And then you finally have a B, and you look at some number of B's, and then you have a C, and you look at some number of C's, and if you're at the end of the string, then you accept, okay? So we can certainly encode that into the Turing machine. Turing machines, in their finite control here, can do anything a DFA can do for sure. So it can zip across the tape here, and here's a space so it knows when it gets to the end. It zips across the tape here and checks that the string is of that form. And then if it's not of that form, what should the Turing machine do? Yeah, it goes into a reject state, because definitely that string is not in this language. If it is of that form, now the Turing machine is all the way at that end, what should the Turing machine do? Yeah, back up to here, okay? And of course it can't accept at that point because it hasn't done anything other than check the basic form of this input. And now it has to start doing something that's akin to arithmetic. Okay. But a Turing machine, it doesn't have a register. It doesn't have registers that can put numbers in there and so on. It doesn't have a built-in arithmetic. We have to encode the logic somehow of how this Turing machine is going to do something that's akin to multiplication. We have to encode that logic into the kinds of rules that a Turing machine has. It has transition functions. Transition function, remember, is a Q cross gamma going to Q cross gamma cross left or right. And then it has an accept state or a reject state, and that's it. So you have to think about how you're going to program such a primitive machine to be able to check whether this number of A's times this number of B's is equal to this number of C's. Okay? So, any ideas? Yeah.
First find the first A, right? And put some number in place so you know where to start.
Okay. All right, and then what? Okay, yeah. Well, yeah, maybe you're beginning along the following train of thought, that what is multiplication? Well, if you have 3 A's and, let's say, 4 B's, okay, so 3 A's. By the way, if I want to write down 3 A's, I mean, not A, but I want to write down that there are 3 A's, would I write it down this way, 3 A's with a apostrophe there, or 3 A's? Anybody have this is sort of a totally unrelated to the course, sort of a grammar, yeah. Top one, bottom one. Okay, well.
The bottom one is proper, but the top one, yeah.
Yeah, okay, so what I was saying, the book does this like that, and when I read it, I instinctively recoiled, saying that that's somehow a misuse. I mean, these are supposed to be, apostrophes are used for possession and for, yeah.
Well, it also depends on how you're using it, because you might want to make it so that it's separate from the 3A. So it's, sometimes it's used for doing plural of something when it's like, the 1950s will be an apostrophe S or something like that.
Oh, they would?
Since we're doing something quantitative, we want to use the apostrophe to separate it from being 3 as.
Yeah, right. No, I mean, I see why people, want to do it. I just wonder what the real proper thing is. Anyway, I don't know the answer, but this is what the book does. But definitely, this is not a contraction or a possession. It's just helpful. Okay.
A to the 3, though.
It's what?
We can just write A to the 3 and not worry about that.
Yeah, right. We could do that, right. A to the 3. All right, well, anyway. So, where was I? Okay, thinking about what multiplication really means. Okay, multiplication means that you're going to duplicate this run of B's. Duplicate is not the right word because you, well, I'll try it anyway. You're going to duplicate this run of B's. So you have 4 B's, okay? And you're going to replicate maybe is a better word. You're going to replicate that as many times as there are A's here, okay? So there are 3 A's, so I'm going to replicate this. I probably shouldn't put... There's 1 replication, and there's the 3rd replication, right? And now I have 12 B's there. Okay, so now what I really want are 12 C's. So what I can think about that the logic of this multiplication is that I'm going to replicate C's, start with 4 of them because there are 4 B's, and for each one of the A's that I see, I'm going to replicate those C's. So I'm going to replicate 3 times, and then I have to check whether the number of C's here is equal to the number of C's here, okay, to find out whether or not this string belongs in this language. So all I'm trying to point out is that multiplication, which we do so instinctively now, at least most of you do, because you did multiplication tables in grade school and so on. I have some certain numbers that no matter how many times I practice them, I just doesn't come up. 7 times 8. I don't know how much that is. I always have to think, let's see, I do know 6 times 8, which is 48, and if I add another 8 to that, that's 56. Okay, somehow that little circuit, that part of the circuit in my brain was cut, and but when you practice multiplication tables over and over again, you get good at doing that kind of stuff. Most people do. And you forget what's really going on is this rather primitive thing of replication. Okay, well, I probably massacred that one. Did I confuse everybody enough? So the Turing machine, now that we think about what multiplication is at a kind of baser, simplistic level, we have a greater hope of actually being able to implement that in the Turing machine. Yeah?
So maybe you find the first A, then go to the first B, and then for every B, look for the same amount of C's.
Yeah.
Once you're done, go back to the A, look for the next A, and go to the first B again.
Right. Yeah. So this is sort of the idea of how it's going to work. Is we're going to read an A, okay, and then we want to cross it off because we want to remember that we've processed that A. So we read an A and we cross it off, and then we run to the B's, okay. And for this number of B's, we want to cross out that number of C's, okay. But we also have to remember which B's we've already processed, so we have to cross them out too. So we're going to cross out a B, run over here, and cross out a C. Okay, so 1 B for 1 C. Then we run back here and we find a B that's not crossed out, and we run over here, we find a C that's not crossed out, and we cross that out and we cross out that B. Okay, we run back, we see another B. Well, let me actually write the right number here. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Run back, see a B. Cross it out. Run over here, see a C. Cross it out. Run back, you see a B. Cross it out. Run over here, you see a C. Okay. Now you're running back, you're looking for a B. Because remember, there's no... The Turing machine doesn't have a register. It doesn't know that there were supposed to be 4 B's in here. All it's doing is going back and forth. If it sees a B, looks for a C to cross out. Okay? Now it's running back here, and it goes all the way through the B's because they're crossed out, and hits an A. Okay? Now what is it going to do? All the B's have been crossed out. What it wants to do at this point is it sees an A, so it wants to go back till it sees the crossed out A, cross out another A, and do exactly what we were doing Okay? For every B in here, cross out a C. But now the B's are all crossed out. Okay? So what does it do? Yeah?
Maybe you should use a different type of crossout for B, so that you can go back there and say, oh, I should set this back to be regular B once I'm done.
Yeah. Okay, so the first part of your suggestion is we're going to use different kind of crossout symbols. Okay? We're going to use a symbol that crosses out A's that's going to be different than the symbol that crosses out B's. Okay? And I don't know whether we need it or not, but just for good luck, let's use a symbol that crosses out C's that are different. Okay? Yeah, I think we need that. So when I go back here and all the B's have been crossed out, okay, and I hit the A's again, the Turing machine at that point, in its finite state control, recognizes that all the B's have been crossed out, and so it can go into a part of the finite state control where it goes back through the B's and turns them back into real B's. Okay? It uncrosses them. And how does it know where they are? Because their crossouts symbol is different than the crossout symbol for C. Okay? So it can just run through the B's, turning them back making them the undead or something. Anyway, these are the, yeah. Anyway, they're back to life. The C's that were crossed out are still crossed out. Okay? The A's that are crossed out are still crossed out. But again, when the back scan that's going backwards looking for an uncrossed out B hits an A and recognizes that all the B, therefore recognizes that all the B's have been crossed out, at that point it can sweep back through the B's, turn them back to real B's. It ends because it hits a crossed out C, and then it runs back till it hits the first crossed out A, and then what is it going to do?
It does it over again.
It does it over again, but say what it is.
Cross out the next A, then goes, looks at the first uncrossed B, crosses it, then crosses out the next C.
Yeah. So now we're back into a configuration where we have one crossed out A and 4 crossed out C's, and that's good. And the B's are back to life. So once the Turing machine puts the B's back to life, it hits this crossed out C, then it can run back till it hits the first crossed out A, goes right, and now it's looking at a live A, and the B's are alive. So it goes back to that part of the finite control, which is going to cross out an A, run to the B's, and then do the zigzag between the B's and the C's. So it crosses out an A, runs to the B's, crosses out a B, runs to the C's, okay? Runs back till it sees a crossed out B, crosses out another B, runs till it sees an uncrossed out C, runs back, runs back, runs back, runs back. Now it's going back looking for a live B. Doesn't see a live B, but does see a live A, and so goes back, turns the B's back to life, hits a crossed out C, so it knows it's at the end of the B's, comes back here, hits the crossed out A, looks right, there's a live A, so does that, then here, 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 and here, okay, goes back, the B's are all crossed out, goes back looking for a live A, doesn't find one, okay, hits, that is it doesn't find a live A, it hits only a crossed out A, okay. At this point, what it knows is that you've used up all the A's, okay, so you've gone through this whole crossout business the number of times equal to the number of A's, and each time you did that, you crossed out a number of C's equal to the number of B's here, okay? So at that point, it definitely knows that the number of C's crossed out is the number of A's times the number of B's. That's the logic of what it did. Okay? And by the way, suppose in this whole business you didn't have enough C's. Okay? Well, you've got to build that into the control too. While it's zigzagging back between the B's and the C's, if it ever runs looking for a live C, a non-crossed out C, but hits an empty space, then it goes into a reject state. Okay? But now, if we've actually gone through, we've crossed out all the A's, so we know that the number of C's we've crossed out is equal to the number of A's times the number of B's. So what should it do now? What? Yeah, it needs to go all the way to the right here and make sure that there aren't more C's. So it goes to the right looking for a C or looking for an empty space. And if it finds a live C, then there are too many C's there, so it rejects. But if it doesn't find a live C, it finds a space, then it accepts. Okay? So I've described this at a high level, and I've shown you some little pieces of how the finite control would work. And all of you should be able to take that description of what I did, and it's basically what the book does too, and actually turn that into written out transition rules, transition functions, which describe exactly what I was doing. And when you do that, or if you write it out as a diagram, you want to group together certain transition rules and say, what these transition rules are doing are the zigzagging, between crossing out a B, looking for the next C to cross out, crossing it out, and go back. So you can describe your Turing machine not just as, here are a whole bunch of rules, now go try to read them and verify yourself, but here are the rules that do this logical operation related to the high-level description of what this Turing machine is doing. And here are the rules that implement the next kinds of logical operation. And here are the rules that move the Turing machine from this kind of logical operation to that kind of logical operation, and so on. And here's the rule that checks to see if there are any additional C's, and so on. Does everybody feel like you could actually do that? Does anybody feel like you want to do that? Good. Yeah, it's something you should do once or twice. Just like programming an assembly language, you should do a couple of times to get a feel for it, and then never do it again. Have a good intuition of what you can do. Okay. So I don't know whether whether the book specifically asks you to do that in any of the homeworks, but I'll put that on the next homework, which should be available tonight or early tomorrow. Right. So there's a question of timing because we have a midterm next week. This is Thursday, next Thursday. So I won't have the homework due on Thursday. It'll probably be due the Tuesday after that. But you definitely don't want to just stop working now just because we're going to have a midterm in a week. So this question will be on it, to actually write up full transition rules, either as literal rules or in a diagram, and make sure that you can actually program this. Okay, so the book has another after that has another example of programming a Turing machine. Yeah.
Just a question on the midterm. What material is going to be fair game for that? Is it going to be like whatever we go over on Tuesday will also be able to be on the midterm, or what we go over this week?
Okay, the question is, what's the midterm going to cover? And certainly everything about finite state machines and PDAs. The question is how much of Turing machines. I would say I would have at least one question on programming a Turing machine, some language, and say, try to describe either as a diagram or in transition rules or a high-level algorithm, but in a way that it's low enough, it's detailed enough that it's clear that could be translated into a real Turing machine. So one question, at least, on programming a Turing machine. And so that really takes us to today's lecture, essentially. But to right now, what we've been doing is looking at the rules of a Turing machine, the mechanics of a Turing machine, and we've done a couple of actual examples of programming a Turing machine. And later what we're going to do today is a theorem and a proof, and so that I would say is sort of the dividing line between the what would be on the midterm and what wouldn't. Okay, that doesn't mean you shouldn't pay attention to the rest of the lecture. In fact, I think today's lecture is the hardest. What's coming is one of the hardest parts of the whole course, so you do want to pay attention to that. And okay, did that answer your question? I'll write that up. And some people have asked for a sample midterm. There's no way I can write one in time. I usually struggle to get the real one done in time. I can find old ones, and they may correspond to exactly where we are in the course, or they may not. And I'll try to find one of those and put those up. Yeah?
Are you going to do like a review on like Tuesday?
A review? Well, it really is up to Sean or you, whether you want to talk about current homeworks or other questions that you have, or whether you want to do a review. I don't know. I don't. The question is, I'm not going to do a review. Yeah. But whether you're going to use your discussion time to do that is really, I think, up to how pressing people feel about the next homework. Okay, so all right. So anyway, the book has another example that it goes into some detail before it moves on to the next topic, which is variance of Turing machines. Anyway, variants of Turing machines. Lots of different variants of Turing machines. For example, first one that the book actually doesn't discuss very many. It does have some in the homeworks. There are other books that I have that have 8 or 9 different variations and things that you can imagine. A Turing machine with a stack, or a Turing machine with multiple heads, or a Turing machine with infinite tape. That's the tapes that we've been looking at are finite at one end. There's a starting point, and then they go infinitely in one direction. But what if you could go infinitely in 2 directions? You can write that way. I mean, there's a starting point where the input is, but you're permitted to write things to the left. Does that help? And in all of those things, when I say does it help, the way we formalize that is whether or not the set of languages that are recognized by this kind of Turing machine is the same, or is it different than the set of languages that are recognized by a Turing machine that has some additional gizmo. Okay? Or is the set of languages that are decided by this class of Turing machines, is that equal or different than the set of languages that are decided by a Turing machine that has some additional contraption? Okay? And two types of Turing machines are called equivalent, or 2 Turing machines are equivalent if they recognize the same language, or if one is a decider, then they both decide the same language. Okay? And so we're going to look at first a variant which has multiple tapes. So you have a finite control as before, and you have a tape, and this might be where the input is, but you also have another tape that you can use, and maybe you have many. Maybe you have K tapes. Okay? K is some finite number. I mean, this is the Turing machine is well described. It has some finite specific number of tapes. Any particular Turing machine does. It doesn't have an infinite number of tapes. But in conceptualizing this class of Turing machines, we don't put a bound on what K is. So there are some Turing machines that have 2 tapes, some that have 3, some that have 16, some that have 1,000. But it's always a specific number. But we represent that specific number as a variable K, or K tapes. Okay? And then what do the transition rules look like? Well, transition rules are, again, going to be what state is the Turing machine in? Okay? What symbol is it reading on tape 1? And what symbol is it reading on tape 2? And what symbol is it reading on tape 3 all the way to tape K? All right? So it's got multiple heads, and therefore it has multiple sources of information. And then based on all of those, it's what state it's in, and what state it wants to move to, and then what it's going to do on tape 1. Is it going to go left on tape 1 or go right on tape 1? Cross what it's going to write on tape 2. Is it going to go left on tape 2 or right on tape 2, etc.? So a very natural generalization. It's just instead of deciding what to do on one tape, it decides what to do on all the different K tapes. And it's going to decide what to do based on what state it's in. It still is only in one state. And what it's reading from all of the different K tapes. Okay? So is this equivalent? The question is a set of K-tape Turing machines equivalent to the set of single tape Turing machines. That is, if you have, i.e., if there is a language recognized or decided by a K-tape Turing machine, is the language also recognized or decided, depending on what kind of Turing machine it is, decided by a single tape Okay, that's what equivalence means. Although actually, from a purely formal standpoint, this is only half of what equivalence should mean. What's the other half? Yeah. Yeah, right. The other half is so trivial we don't even put it up. But formally, it is the other side of this question. Is there a language, if there is a language that's recognized by a single tape Turing machine, is the language also recognized by a multi-tape Turing machine? Well, yes, because a single tape is also a multi-tape. I mean, it's where the k is equal to 1. So that's fine. The class, anything that can be recognized by a one tape, any language that can be recognized by a one-tape Turing machine can certainly be recognized by a two-tape Turing machine. Okay, what does that two-tape Turing machine do? It just ignores the second tape. It runs exactly like the one-tape Turing machine does, and just ignores the second tape. I mean, if you had a two-tape Turing machine and you were literally writing out the transition function for it, you would always have to include in the transition function that no matter what is on the second tape, well, in fact, the second tape will be empty because you never do anything with it. You just do nothing with it. Okay, but at any rate, certainly anything that a single tape Turing machine can do a 2-tape Turing machine or a 3-tape Turing machine or whatever can do. Okay, but this direction. So this direction is the interesting one. So what do people think? Are 2 heads actually better than 1? Well, not in this context. No, 2 heads are not better than 1. 2 tapes are not better than 1. You can simulate. So question, is the set of tape equivalent? And the answer to the question is yes. Okay? And the proof of that is that we can simulate any computation of a K-tape Turing machine with a 1-tape Turing machine. So this gets into the first of what's a really important concept in Turing machines and the study of languages is the idea of simulation. All right. So what do we have to do in order to prove that we can simulate any computation of a K-tape Turing machine with a 1-tape Turing machine? We have to, what we, the provers, have to do is describe in some generality that if you ever had a multi-tape Turing machine, and you have its transition functions and its multi-tape, let's just say, for the sake of the picture, it's 2-tape Turing machine. So given a description, given a complete specification of a 2-tape Turing machine, we want to come out with a specification of a 1-tape Turing machine where we can prove, or at least usually it's pretty obvious, that any computation that's done on this 2-tape Turing machine will have an equivalent computation on the 1-tape Turing machine. And so this computation will end up in an accept state if and only if this computation ends up in an accept state. We want to be able to go both directions, if and only if. Okay, so what's the idea of this simulation? The idea is that the 1-tape is infinite. So we've got plenty of room. We're never going to run out of space. We can always grab more space if we need it. All right? So the 1-tape, the single tape, is going to basically encode. Let's just, for the sake of clarity, first just talk about a 2-tape Turing machine. So I want the single tape to be able to always write down on its 1 tape what the contents of the 2 tapes are in any kind of computation that the 2-tape Turing machine is doing. Okay, so here's the 2-tape Turing machine. Here's tape 1, and here's tape 2. Okay, and tape 1, let's say that's on 1 tape is where the input comes, and the other tape starts empty. But as the computation goes on, tape 1 can have something other than the input because the Turing machine can write onto it, and this tape can have things on it too because the Turing machine can write onto it. So at any given point, there is something that's written on this tape. I don't know what it is, A, B, B, A, C, whatever. But it's a finite amount. It's not, even though the tape is unbounded, it's infinite. What's written on the tape at any given moment is some actual finite number of symbols. So it ultimately hits a blank. And the same thing over here, B, C, A, B, C, whatever. Finally some blank. All right. So, and then as the Turing machine progresses, it's in some particular state. It still only has a single state that it's in. Okay, multiple tapes, but it's the same kind of finite control as before. So what do we want the simulating one-tape machine to do is to have on its tape the contents of tape 1, AA, BB, A, C, down to there, then some kind of mark which says, that now I'm going to be writing the contents of tape 2, B, C, A, B, C, down to there. So I have to tell you how we're going to update this because it looks a little compressed. What happens when you do in tape 1, what happens when you write something into its space? This is only going to be a single space here, all right? This isn't infinite. The first part can't go forever because then there's no room for the second tape. So we only have a single space here. And what happens if in this computation we write something into that space? Down here we want to write that in that space and put another space there. Okay, but you can't insert into a tape. A tape is a purely sequential thing. Well, what can you do? Are you scratching your head or are you answering?
I think maybe you could add it after the second one.
Okay. Anybody have another suggestion? Yeah.
You insert, actually you copy everything.
You can move. It's tedious, but you can move everything down. Okay. You can, if you're, remember this has a finite control in here, and it's going to write something. It wants to write something into this space. That's fine. It writes it there. But now it wants to put another space there, and there's no room for that. It can enter a part of its finite control where it moves everything to the right, one space to the right. Okay? How does the Turing machine do that? It runs till it hits the end. Okay? Now this one is only 2 tapes, so it runs to that blank. Okay? And then it backs up by 1. Let's see. Moves that over. Yeah. Well. Okay. Yeah. It finds the blank, moves over by 1, writes that there. Okay, and puts a blank there. Then goes to the left until it sees a character, writes that there, puts a blank there, and so on. Okay. So it's tedious, but you could certainly write the finite state rules. It's tedious for the machine. For you, it's not that difficult to write the rules that would move everything on a tape one space to the right. So think of that as a subroutine or procedure or whatever. A small computation, small part of the Turing machine program that just looks at the small task of moving everything one place to the right that's written on a tape. And you should see that that's a very simple thing that a Turing machine can do. So if it ever needs more space on some portion of this tape, it can move everything to the right by 1 space. Fine. What else does this Turing machine need to know in order to represent a computation that's happening in this Turing machine? So we can write the contents of both of these tapes on a single tape, but we also need to know where the read heads are. We need to know where the read head is for tape 1 and the read head is for tape 2. Okay, this single Turing machine with a single read head, for every step of the computation that this is taking, we want this machine to do some computation which ends up simulating what that single step was over here. Well, the single step over here can move both of its read heads. okay? But this one only has a single read head. So we have to encode that somehow in the tape as well. And the way the book describes this is that you can put a mark on the tape over a character where the read head is positioned on this machine. So this mark, this dot here above a character, represents the fact that the read head for tape 1 is sitting over this character B. And the read head for tape 2 is sitting over this character C. All right? And that is it's a mark that the finite control can use when it's deciding what to do over here in terms of simulating that, because it knows where the read head is for each of the two machines. Now that mark sounds magical. How does the Turing machine, remember, this is a Turing machine that only operates through its transition function. So you have to specify exactly how a Turing machine can do that, and it has a tape alphabet as well. Okay? So any ideas of how we can implement a mark?
It's expanded alphabet.
Yeah, right. What were you going to say back there? Yeah. You have under your control when you build this Turing machine. So remember, we're looking at this. Somebody shows me a two-tape Turing machine, and my job is to create a one-tape Turing machine which can simulate this. Whatever computation this goes through, this will go through some computation which ends up simulating this. And I can use whatever alphabet I want. It's got to be finite. The input alphabet is going to be the same, but my tape alphabet can be different. Okay? And in particular, I can have an alphabet that's twice as big, a tape alphabet that's twice as big as this tape alphabet. The tape alphabet's used here. So I can have a tape alphabet here which contains all the regular symbols, characters that are used here, but in addition has the same characters with a mark over it. Okay? So it's an additional character which, instead of just a B, we have a B with this mark over it. Okay, so you can think of the difference between lowercase or capital, or a character that's in italics versus not italics, whatever you want to think about it. We'll just have a richer tape alphabet that can put a mark. But logically thinking about it, or at least the way the book describes it, it's putting a mark over a character to represent where the read head is on this computation. So the point is that this single tape, can represent exactly what is the status of any computation that's happening here. We know what the two tapes look like, we know where the read heads are, and then we build into here a finite control which corresponds to the transition rules that are here, and does the appropriate thing on these on this single tape, moving things down if necessary in order to get enough space. Okay, so if I was going to take this idea all the way down to a real program, I would show you an example of a 2-tape or a 10-tape Turing machine, and then show you the actual transition rules. But we're past that point where we're doing all the gross details, mostly because they're so gross and so tedious. It would take many lectures, and you probably wouldn't all absorb them anyway at that detail. You'd have to go back and think about it yourself. But here's the general strategy. And if we put the word proof over that description of that strategy and then put a QED at the bottom of it, then we've pretty much done the way the book did it, and say that should convince you that whenever you see a multi-tape Turing machine, you could create a single-tape Turing machine which recognizes the same language, because this single-tape Turing machine is simulating. On any computation this does, this will just simulate it. And if this enters an accept state, so will this. If this enters a reject state, so will this. If it doesn't enter either, then neither will this. Okay. So we have the first theorem about Turing machines, which is that multi-tape Turing machines are equivalent to single tape. Okay. As I mentioned earlier, there are many different variations of Turing machines. Tapes that go in both directions, push-down stacks, and so on. And for each one of those, people have come up with proofs to show that those are equivalent to just the standard Turing machine that we defined here. A single tape, unidirectional tape Turing machine that is any language that one of those more exotic Turing machines can recognize. Then, so a single tape Turing machine of our basic type can recognize also. What's the next? Can anybody suggest what the next variation that might be important, or that might get us out, possibly get us to a class of languages that strictly contains the languages that are recognized by single tape Turing machines? Any suggestions? Yeah. Multi-dimensional tapes. That's sort of like, yeah, so that's sort of like multi-tape Turing machines, but you can move more freely between tapes. Yeah, up, down, left, or right. Yeah, people have thought about those kind of things, and they're equivalent to the single tape. You can simulate those as well. Yeah.
Maybe a counter?
A counter might be useful. People have thought about machines with actual numbers and shown those are equivalent. Anything else? Yeah. Multiple head for the same tape. Yeah, that would be sensible too. So you could read different places on the tape at the same time, and all of those things would make the machine more efficient. It could run faster, do the computation more quickly. But when you start thinking about these things, you realize, okay, multiple heads, we could, because we have this marking alphabet, remember? We can put marks, and so we can simulate what a multiple heads would be doing with just a single head and a single tape. So that doesn't get us out of the class of languages that are recognized by single tape Turing machines either. But there's one big one, yeah.
What if you didn't require the set of states to be finite?
If you didn't require that the finite state be finite, yeah. And what do you really mean by that?
I'm not quite sure.
Okay, well, that's good.
To be an infinite set rather than a finite set.
Okay, and that does get us outside the game plan. Yeah, we're always in the finite control. The number of states there in our description of the Turing machine is finite, and I don't know what an infinite state machine looks like, although I'm sure that people have thought about it, and that I think really would get us outside the game we're talking about. But yeah, so that one we don't allow because we are trying to represent ultimately what real computers and real computation does. Yeah, you had a suggestion.
Is it non-determinism?
Right. The big kind of the two flavors of finite state machines that we looked at when we were talking about finite state machines were deterministic and non-deterministic. Okay? And when we were talking about finite state machines, deterministic meant that the transition was a particular state, a particular symbol that you saw on input, and you went to a very particular state. Okay? in finite state machines, you had no ability to write onto anything, and you always moved to the next character, so there wasn't a question of left or right movement. And this was deterministic because this is only a single specified state. In the non-deterministic, you went to a subset of states. This represented the power set, the set of all subsets. And so for any particular state that you were in and any particular symbol that you were reading, you went to some subset of states that were permitted. And then when we thought about the actual computation of non-deterministic finite state machine, we said whenever there were choices, we basically replicated that machine in as many ways as there were choices, and each one of those different replicated machines took a different choice. So in a sense, we were doing all those computations in parallel, and then the finite state machine ended up accepting its input if any one of those replicated paths of computation ended up accepting, and it rejected if they all ended up rejecting. Well, and then we proved that, yes, okay, we have all this descriptive power in non-deterministic finite state machines, but it really was no more powerful than deterministic finite state machines, because any non-deterministic finite state machine could be converted to a deterministic finite state machine. So the class of regular languages that were accepted, or the class of languages that were accepted by deterministic finite state machines and non-deterministic finite state machines, those were the same. Okay? So it seems sensible that we would want to explore the same question in the case of Turing machines. We would want to define what a non-deterministic Turing machine is, and then ask, does a non-deterministic Turing machine have more power than a deterministic Turing machine? That is the class of languages recognizable or decided by non-deterministic Turing machines, does that strictly contain the set of languages that are recognized or decided by deterministic Turing machines? Okay, a lot of words. So let me specify what a non-deterministic Turing machine is, and then we'll get into the question of equivalence. So in a non-deterministic Turing machine, so we know what we have to do to specify what we call a Turing machine. And so if I say Turing machine, that will usually mean deterministic Turing machine, though sometimes by context, if the context is absolutely clear, it might be a non-deterministic. But for right now, I'll try to make that distinction always explicit. So we know what we need in a to specify a deterministic Turing machine. It's the 5 or 6 things that I put up before. We need the input alphabet. We need the tape alphabet. We need the start state. We need to know what the accept state is. We need to know what the reject state is. And then the most important thing of all is we need to know what the transition function is. Okay, so this goes to right? So this is the basic information you need if you're going to specify, and this is many of them, of course. Well, this represents all of the different transition. This represents the transition function, which contains in it all of these different transition possibilities. For a non-deterministic, just the same way that we define non-deterministic finite state machines, what do we now want to do to define a non-deterministic Turing machine? Yeah.
We just do the power set.
Yeah, you just do the power set over here. So this is some subset of this triple. Okay, this is a triple which says state, what you're going to write, and where you're going to move. And so this is saying, if I'm in state, let's say 7, and I see a B, on my tape, okay, then instead of just one thing that I'll necessarily do, there may be several. It may be I move to state 9, and I write well, let's say a Z, and I move right. Well, that's one rule. But another one would be to move into state 15, write a Q, and move left. Okay? And there may be more than 2 possibilities. So there are choices. So that's the specification of a non-deterministic Turing machine. What does a computation of a non-deterministic Turing machine actually do? Well, it does pretty much what you would expect it to do based on all of what we did when we were thinking about non-deterministic finite state machines. That is, as the computation of the non-deterministic Turing machine proceeds, when you're at a point, when the Turing machine is at a point where there are choices, the Turing machine replicates. If you have 2 choices, then you have 2 Turing machines. One of those Turing machines takes that action, goes into state Q9, writes a Z and moves right on its tape. And the other Turing machine, the other copy or replicate of that Turing machine, goes into state Q15, writes a Q and moves left. Okay? And if there are more than 2 choices, then we'd replicate into more than 2 different Turing machines. Now, each one of these replicates can spawn off additional replicates and so on. You can get a large tree of possible of Turing machines, replicated Turing machines, and different computations that are happening along that different paths in that tree. So so here's the sort of the picture, or maybe I call it a cartoon, of a computation of a non-deterministic Turing machine. It's got one machine, it's starting, and then it hits a place where it can make 2 different choices, so now it replicates into 2 machines, and then this machine, in this computation, hits a place where there are 3 choices, let's say, and so it replicates 3 times, and they each make a different choice. Maybe this one goes on for a ways without, its computation goes on for a ways without hitting a choice. It's deterministic, and then it finally hits one where there are 7 different choices. Why did I say 7? I don't know. It's a lot of boxes. Okay, 7 boxes. So a tree, you have a tree of computations which happens when the non-deterministic Turing machine does its computation. Now, in each one of these computations, ultimately, well, in each one of these computations, what happens? That computation either hits an accept state or a reject state, or it could go forever. That computation could go forever. So maybe we come down to an accept. Maybe this one ultimately comes down to a reject. And maybe this one just goes forever. Okay? And never terminates. So we say this, the non-deterministic Turing machine, accepts if any one of these different spawned-off machines ultimately accepts. Okay? So, and again, this is really the same thing we were saying when we were talking about non-deterministic finite state machines. Okay, so the non-deterministic Turing machine accepts its input if any of the spawned computations accepts, or enters an accept state. Okay? And it rejects if every spawned computation enters the reject state. Okay? And it goes forever, or does not terminate, if any of the spawned machines or spawned computations does not terminate, okay, let me stop there for a minute. Does this make sense? If I wrote this up this way? No. Who said no? Yeah. And why?
Because you could have a single non-deterministic Turing machine, both accept and go forever.
Yeah, right. So this can't be the end of it, because here I'm saying the non-deterministic Turing machine will accept if one of its spawned computations ends up in an accept. Well, some of the other spawned computations might go forever. Okay? So I don't want to say that I don't want to leave it like this, where it says it doesn't terminate if any of the spawned computations does not terminate.
Shouldn't be and is not.
Yeah, and I don't want to use.
Accepted.
Yeah.
I guess which one takes precedence?
Well, acceptance should take precedence.
Okay, I've gotten myself into a grammatical corner here. I wrote something that I want to change, but in order to change it correctly, I have to change the grammar. It does not terminate, first of all, if no computation none of the spawned computations accepts. Okay. And some computation does not terminate. Okay. So, and you could kind of, I think formally you could remove this, and the first two would imply that we accept when any of the spawned computations accept, we reject if every spawned computation rejects, and it's possible that neither of these two things happen, in which case the termination doesn't terminate, and that's really what's written here. Okay? But these two things imply that one. All right, so now we know what a non-deterministic Turing machine is, how you specify one, and this talks about what the computation looks like, and this talks about whether the machine accepts, rejects, or doesn't terminate. So now we can think of the class of languages that are recognized by a language is recognized by a non-deterministic Turing machine. Let's give it a name, N, if for every string in the language, let me give the language a name, let's say A, for every string in A, N accepts the string. Okay? That's what it means to recognize. Now, we talked about a different concept previously. A language A is decided by a non-deterministic Turing machine, call it N, if N recognizes A and something else. What's that something else? Well, recognized means that whenever the string is in the language, the non-deterministic Turing machine accepts. There's some computation. It can spawn, and one of those computations is going to end up accepting. Okay? A language A is decided by a non-deterministic Turing machine if it recognizes A, which means whenever there's a string which is in the language, this non-deterministic Turing machine will accept. But here I didn't say what happens when there's a string that's not in the language. Okay? So what can happen typically when the string is not in the language? Yeah?
Just sit somewhere in a state and go on forever.
Well, it could either reject or it could not terminate. The computation might not terminate. Okay? So the distinction between a recognizer and a decider is that the computation always terminates. So the and I want here is that if a string, an input string, is not in A, then the Turing machine, the non-deterministic Turing machine, will reject the input. So this recognizer has the possibility that it doesn't terminate. It always terminates when given a string that actually is in A. It terminates by accepting. But here we have the possibility that, but it has the possibility of not terminating. Here we get rid of that possibility. Yeah.
When it says N wants to reject the input, is it rejecting the string or the language?
No, any non-deterministic Turing machine, when it's given a particular string, just accepts, rejects that string, or computation doesn't terminate. So a Turing machine treats a particular string, or when it's given a string, it computes on that string. When we talk about accepting a language, well, the first time we used that, the book slapped us on the hand and said, don't do that. Always talk about recognizing a language. So a Turing machine, or a finite state machine, or now a Turing machine, recognizes a language, means it accepts the set of strings which are in that language. Did that answer your question?
Kind of, I think.
Okay, so we have the word accept. That's talking about a specific machine with a specific input.
Well,
We have the word recognized.
I'm talking about that last phrase in which you wrote or.
Yeah.
The string is not an A, then N will reject the input. What do you mean
Yeah.
by the input? Is it the string or is it the language?
Okay, yeah, the string. Let's give it a name. W is not an A, then N will reject the input W. Yeah, so when I had string here and input, I meant for them to be the same thing. Thanks for clarifying that. Yeah, input and input. Okay, so now that we have these definitions, we can ask the equivalence question again. No, it was over here before, but all right. We asked about equivalence of multi-tape Turing machines and single-tape Turing machines, right? We had something over there which literally said, if a language is recognized by a multi-tape Turing machine, is it also recognizable by a single-tape Turing machine? We had that question, and we answered yes. Now we're going to ask the same question about non-deterministic Turing machines and deterministic Turing machines. So here's a question. If a language is recognized, or we could be thinking about decided, by some non-deterministic Turing machine, N, is it also recognized by some Turing machine? Well, I'll put a D here just for emphasis that now we're talking about a deterministic Turing machine. Is it, and what is it? It means the language. If a language A is recognized by some non-deterministic machine, is A also recognized by some deterministic Turing machine? So this is again the same question the same kind of question that we had when we were talking about single tape versus multi-tape, single head versus multi-head. We have something that looks like more power. Because of non-determinism, we have this ability to operate in parallel. When we were talking about finite state machines, we saw that that non-deterministic finite state machines were in fact no more powerful than deterministic finite state machines. When we were talking about pushdown automaton, we didn't talk about non-deterministic pushdown automaton. It turns out they are actually more powerful than deterministic ones. We didn't do that. So non-determinism and determinism are not always the same. Well, what do you think about for Turing machines? Does non-determinism give you more power in this sense, in the sense of this question? What do you think is the answer to this question?
No.
Okay, that's one possible answer. No. Any other possible answers? Yes, that's another possible answer. Okay. And do you have an intuition for why you say no?
Well, just my intuition.
Okay, it's just a hunch. Okay, yeah.
Well, I would think no, because since the string is of infinite length, you could just, whenever you needed to spawn a copy, you could copy the entire string over into a new section of the blank area and separate them by a certain symbol or something. And whenever you needed to spawn more copies, maybe just use multiple occurrences of that given symbol or a different symbol.
Okay, it sounds like what you said the answer was no, but it sounds like you were giving an explanation for why the answer is yes. Which specific answer do you want to this specific question?
Oh, yeah, I meant yes. Okay, yeah, I meant like there would be the same, like the non-deterministic would not be more powerful.
Okay. Another suggestion?
Based on that idea, I would think that if you're talking about decided, then the answer could be yes, but not if you're talking about recognized, because if you entered like an infinite loop in a particular string, then you would never be able to like leave that computation and move to the next computation down the input tape.
Yeah, okay, so we've had three good suggestions, yes, no, and maybe. Okay, and the maybe one is recognizing a real technical subtlety. So the yes answer was kind of an outline of how we could simulate a non-deterministic Turing machine with a deterministic Turing machine. The maybe answer is pointing out that simulation has got a problem where when you're going down one particular computation, if that's a computation that doesn't terminate, your simulation could get in trouble and not terminate as well. And that is actually a real problem and one that is addressable. So the answer is actually yes, but with cleverness that addresses exactly the problem that was raised here. So there's a really good initial reactions to this question of seeing that subtlety. And so this is what we'll do next time, is I'll show you in detail how you can simulate a non-deterministic Turing machine with a deterministic Turing machine and get out of that pitfall of possible non-termination.